Okay, hi everybody. I hope everybody had a very nice Thanksgiving. I'm going to start today with just a quick review of what we talked about before the break. We were talking about Chapter 9. Okay, so just trying to understand motion, try to understand mechanics within a non-inertial reference frame. Alright, so just as a reminder, we first started off with just talking about a object which is uniformly accelerating, perhaps a train, right, and trying to understand motion within that train. Okay, so to do this, what we talked about, I guess a week ago, was describing a inertial frame, which we call S0. Right, this is at rest. It is not accelerating in this case. Right, so it's just an inertial frame, and then the train is moving within that frame, and we can also create a frame which is moving with the train, which we call that S. Oops, sorry, my artwork is not so good right there. Okay, so this frame S, is accelerating with acceleration capital A, right? Or we can also say it has some velocity v at any moment. And I'm going to use big capital letters for the acceleration and the velocity of that frame. All right, so if we want to talk about the motion within this frame, all right, we can also talk about, I always talk about the velocity relative to the inertial frame, right? So we'll use a little sub-zero here, and that's equal to the velocity within our moving frame plus the velocity of our moving frame. All right, so this is just relative velocity equation, right? The velocity in our inertial frame, the velocity in the non-inertial frame, plus the velocity of that frame. Okay, and we can also write this in terms of accelerations, of course. All right, so the acceleration in our inertial frame is equal to the acceleration observed in our non-inertial reference frame plus the acceleration of that frame. Okay, so that's not so bad. And as you recall, we last time multiplied both sides of this by m. Okay, and then we just rearrange this to solve for the mass times the acceleration in the moving frame. Okay, and what we recognized last time is that this term is just the sum of the forces acting on that object, right? This is just Newton's second law. It still holds in the inertial frame, so therefore the mass times the acceleration in the inertial frame must be equal to the net force acting on that object. And this term, we gave a name, we called it F inertial. Okay, so we can still work with Newton's laws in this non-inertial reference frame, but now we have this extra term, right? The observed acceleration in the non-inertial frame is equal to the net force acting on the object minus this mass times the acceleration of that moving frame, right? So this is extra term. So this obviously is some kind of fictitious force, but it has real effects if you're in that non-inertial frame, right? If you're in a train that's accelerating rapidly, you're going to feel pushed back into the back of your seat, right? A backpack on the ground is going to slide to the back of the train, right? If you have positive acceleration of the train, positive acceleration of that frame, you can have this fictitious negative force, right? Or if the train slows down all of a sudden, you're going to have a moving frame with negative acceleration. This will be a positive fictitious force, and your bag will slide to the front of the train. Okay, so within that non-inertial frame, there are real effects from, this accelerating frame. All right, so this is a linear example. We're going to do a lot of other examples in this chapter, including some fun ones, including trying to understand the tides. Right, so the Earth is not only spinning about its axis, making it a non-inertial reference frame, but it's also orbiting some common center of mass with the moon. So that's going to lead to a bunch of fun effects. And then, of course, the spinning Earth is going to result in things like the centrifugal effect and the Coriolis effect. So we'll work to understand those.